All right, this video is going to go over problem 4.6, that last problem from chapter 4 that we didn't have time to get to in class. Again, a trapezoidal channel problem. We're going to use the Manning equation, except for this time we're solving for slope. We know velocity, but we want to find the channel's steepest allowable slope. We also know that it's an earth channel, that it's grass lined, and that it's mown, and then we can look at our Manning's numbers from our textbook, or I will give you that number, but just looking at the chart here, the Manning's n for that is 0.030. So we'll use that Manning n for this problem. And then we're also given information about the channel itself here, as well as the maximum velocity, which is 6 feet per second. So let's take a look at the channel dimensions here in terms of our trapezoidal channel information that we derived in class. So remember, we came up with some formulas using similar triangles and Pythagorean theorem about how to find the area, width, wetted perimeter, and hydraulic radius. So we said if you call this top measurement here, that's the top width of flow. This bottom width is the variable b. Y is the depth of flow, and m is the horizontal component of a side slope ratio, which has horizontal to vertical components. If those definitions are true, then we can say that the area is equal to by plus my squared. The wetted perimeter is b plus 2y times the square root of 1 plus m squared. That top width is equal to b plus 2my, and the radius is the area divided by that wetted perimeter, that hydraulic radius that we need for the Manning equation. So let's go ahead and write that Manning equation down, and then we'll also write down this information for the trapezoidal channel. So Manning equation from the handout is that our velocity equals this 1.486 conversion factor divided by that Manning's number n times hydraulic radius to the 2/3 times slope to the 1/2. So in order to find that hydraulic radius, we're going to have to find out some information about this channel. So we're given that that depth of flow is 2 feet, so we'll call that the variable y. The side slope is 1.5 to 1, so we'll call that horizontal component the variable capital M. And then we also know that the base has this width of 3 feet, so we'll call that capital B with our variables here. And so the first thing we're going to do is go ahead and find that area. And so from the formula sheet, we're told that area is equal to by plus my squared. And so we'll take our b, which is equal to that 3 feet times 2 feet plus the m, 1.5 feet, times the y, which is the 2 feet, and we have to square that term. Oh, that 1.5 is not feet. That's just 1.5. That's just a ratio. And that's how I wind up with feet squared here and feet squared here. And so that's equal to 12 square feet after the math there. And then the wetted perimeter, again, we're going to follow those formulas. That's equal to this base b plus 2 times y times the square root of 1 plus m squared. So in this instance, we have 3 feet plus 2 times 2 feet times the square root of 1 plus that 1.5 squared. Remember, 1.5 does not have any units in this definition. And so we find out that that wetted perimeter is 10.21 feet. So in order to find the hydraulic radius, we're going to take that area and divide it by the wetted perimeter. Area divided by wetted perimeter, and we get 12 feet squared divided by 10.21 feet, so we will get an answer out in feet, and that is 1.175 feet to 3 decimal places. So now we're ready to substitute into the equation. We know velocity, we know Manning's number n, we know hydraulic radius, and we're looking for slope. Always a good idea to solve algebraically first, but nobody ever seems to want to do that. So I'll go ahead and plug numbers in. That'll work out okay for us too this time. One thing about putting units into this equation is that because of our conversion factor and our exponents here, it gets kind of crazy. So oftentimes when I use this equation, I just put the numbers in, but I know that when I put velocity in, it has to be in feet per second. When I put hydraulic radius in, it has to be in feet. So v is just equal to 6 here, and that's 1.486 divided by the 0.03, and then I'll call that r 1.175 to the 2/3, and then some unknown s to the 1/2. Now let's move some numbers around so we can solve for s. I'm going to take that 6 and multiply it by that Manning's n, and then divide it by the conversion factor there, as well as that hydraulic radius raised to the 2/3. And we'll set all that equal to slope to the 1/2. All right, after I do that math, I do wind up with, slide that down so you can see it, 0.1088, and we'll say that's equal to that s to the 1/2. So I want to unpack that s and not have it to the 1/2. I just want to solve for s. The way I'm going to do that is square both sides. Okay, that s to the 1/2 squared, those cancel each other out. I'm wind up with s on this side, and then if I take that 0.1088 and square it, I wind up with 0.0118. But I am not done yet, because this is asking me for a slope in a percent to 1 decimal place. So I can take that slope number and multiply it by 100, which is going to give me 1.18% slope. But then remember, I'm also asked to round that to 1 decimal place, so I'm going to call that slope 1.2% for a final answer.